We will touch on. I have the homework here. I've got it right here. Chapter 20 homework. So eventually we'll pull this up and look over a couple of these, make a few comments on the homework, and get you going on that. Okay, here is second order in one reactant. So this would be, well, this could be whatever. I want this right. Oh, I thought maybe you won the match, and
no, I didn't win the match.
It was going on to another tournament.
I definitely didn't win the match. That's right.
So here is this sort of situation where you might have its second order in A, and that would be the expression for it. The decrease in A, change in A with respect to time is equal to the rate constant times the concentration of A squared. And rearranging that is like we did with the first order equation, and deriving it and taking the integral of this, taking the integral of both sides of this equation, you get down to something that starts looking like this. And so this would be, well, both of these would be ways of expressing the second order rate equation.
So it's second order with respect to A, meaning the exponent's going to be 2. Doesn't that, the coefficient then, where does the coefficient of 2A go? Does that have anything to do with any rate?
No.
Even with the derivative of...
This is coincidental.
Okay.
That the coefficient, that the power, the order, and the coefficient are the same.
Right. So, but my question is with that is, so if the coefficient is 2, I thought that negative dA divided by 2 dt equals rate.
You're right. Wait, okay, all right. I probably didn't write this one very well. Very good, Liz. Yeah, it should have been that. It would have been minus 1/2 dA over dt. Right. Very good. Okay, so it doesn't matter what that coefficient is. Yes, this is how you would write that, because you would have that this, the rate of change of A with respect to time, is equal to the negative, the rate of the change of B with respect to time, which is equal to positive the rate of change of C with respect to time. Yeah, we'll get some other examples of that. The coefficient does come in to this part of the equation. Yes.
Okay.
Thank you.
So then, like the rate equation that we learned in Gen Chem, we never had to worry about coefficients, right? For like the concentration. So I mean, like when we're looking at the actual rate, there should be a 2 there if there's a 2. But I guess does the coefficient just get built into K? Do you see what I'm saying? So like when we're doing rates, we're not worrying about the coefficient on there. So like the homework assignment that we had, there's a couple that had a coefficient, and I was trying to figure out.
You like the first one?
Yeah.
Right.
I was trying to figure out, does this actually matter? And I looked it up and said, no, don't worry about the coefficients.
And then the answer had a coefficient, or had.
No, I don't think it did.
Okay. Okay.
I guess does the coefficient always just get built into K? Is that like a way that?
Are you talking about 1 on the homework?
Yeah, I think so.
Oh yeah, I had trouble with number 1 as well. I think he's going to go over it.
Okay.
I didn't get an answer that agreed with 1 on the back.
Let's do that right now, since it's kind of relevant here. Here's a pretty complicated equation with a whole bunch of coefficients. 2 chloroform plus 7 hydroxide yields carbon monoxide, formate ion, 6 chloride ion, and 4 water. Okay, so there's a pretty complicated equation. And this is saying let K be the rate constant for the rate of the reaction of the hydroxide ion. All right, so in kinetics you do need to refer to what are you talking about? What rate are you talking about? And if we went in here and said, okay, what are these rates? We could say that just like what Liz was saying, we would pull these coefficients into this part of it. 1/2 times the rate of change of the, and I'll try to write here a little nicer, minus 1/2 times the change in the chloroform with respect to time is going to be equal to 1/7. If you had a rate of disappearance of chloroform, 2 chloroform react with 7 hydroxides. So there is going to be this relationship between the rate of disappearance of chloroform relative to the rate of the disappearance of the hydroxide. We're not getting into the order. This isn't the order of the reaction. This is the stoichiometry of the reaction.
Is the other one, aren't these the same?
Excuse me, there's got to be a negative here.
Yeah.
Yep.
Negative and negative.
Yeah, we're talking about disappearance, negative, and that's going to be equal to positive the appearance of carbon monoxide, which is going to be equal to positive the appearance of the rate of the appearance of the formate, which is going to be equal to positive the 1/4 the rate of the appearance of the water. All right? There is a relationship between the rate of reaction of each one of these things involved, each reactant and each product, and they are related according to the stoichiometry. However, the kinetics is proceeding. When 2 of these react, 7 of those are going to react. Okay, that's kind of given by the stoichiometry and irrespective of the kinetics. So what could we say here? We've got we're going to say that we want to set up an equation that expresses the rate of this reaction with respect to the disappearance of hydroxide. So we're saying that the disappearance of the hydroxide ion with respect to time is equal to K. Okay, now let's finish this off. What else are we given? The reaction was found experimentally to be first order in chloroform and first order in hydroxide ion. So what is the rest of this rate equation? The disappearance of the hydroxide with respect to time is equal to this constant. This is the rate constant for the reaction of the hydroxide.
Well, so
It's first order in chloroform.
Chloroform to the first, and then
Okay, so it's going to be times the concentration of the chloroform to the first power. The reaction is found to be first order in chloroform and first order in hydroxide.
so you do hydroxide. But
So you got to multiply it by the hydroxide.
yeah, we're looking for the rate of disappearance of.
Hydroxide.
Yeah. So then, where is this 7 going.
Okay, now let's see. Let's go on there. Okay, are we okay there? That this would be the right expression to represent the rate of the reaction of the hydroxide. This is a K that's associated with the reaction of the hydroxide.
Isn't it CHCl3?
Did I just keep saying that?
Granted, it doesn't matter.
What does?
I mean,
One of them's a carcinogen and one of them probably isn't.
yeah.
Okay, thank you.
Yeah.
Carbon tet is. Lots of halogens are. Okay,
I guess I'm a little confused on like the in terms of hydroxide ion, and how are you making like the rate on the left with respect. So they're saying that the rate of the reaction is first order to both of those two things, right? Is that like directly related to the DOH dt?
yeah.
Did you say?
Yeah, it is first order in chloroform and first order in hydroxide. This governs, it's first order in two reactants, it's second order overall. Those things are going to govern the rate equation. These two things you can't really write a rate equation here irrespective of the chloroform.
Okay.
It's going to affect the rate.
And same with the hydroxide.
And same with the hydroxide. So if we're saying, okay, what is the rate at which the hydroxide ion is going to change with respect to time, it's going to be a constant times whatever that concentration is initially times whatever the hydroxide ion concentration is initially.
So if I was thinking to set this up, I would have put 1/7 in front of DOH dt. Negative 1/7, because it's like so the rate is I would think the rate is like the formation of CO, right? Which there's only one for every.
It says in terms of the hydroxide ion.
You know, this is how all of these rates relate to one another. This 1/7 that rate equals that rate.
Okay.
Okay, now let's look here. Let's say write a rate equation for the chloroform. Okay, so there is the rate. In terms of this hydroxide ion constant, rate constant for hydroxide ion. So let's look at that. Minus 1/2 dCHCl3 over dt equals negative 1/7 the change in the hydroxide ion with respect to dt. Okay? So now let's multiply both sides by 7. I'm going to multiply this by 7. I'm going to multiply this by 7. And I'm going to get that the negative 7/2 the change in the chloroform with respect to time equals okay? We said this up here, so I'm just saying it again down here, and getting an expression now that says what this rate is equal to in terms of that rate. So now if I want to rewrite this in terms of the methyl chloride, it's going to be this, is that right, we set up here, this is equal to that. That's the rate of the hydroxide ion, the change in the hydroxide ion concentration with time is equal to that. We've just said that this is equal to that. So now this is equal to that. Or we could, or just say that hang on a second here. I'm sorry, wait a minute. Yeah. We can actually take that, Yeah, so we can multiply this by 2/7 and would get that. I just keep wanting to call this, that would be methylene chloride or methyl chloride. This is chloroform. Okay, so there you go. There's the expression in terms of methyl chloride. And we already wrote the one with respect to hydroxide, and now it would just be, you could go off of all of this up here, this here, and get an expression for carbon monoxide, get an expression for formate, get an expression for what? Status for water? No. Okay? Liz, does that cover number one?
Yeah, I got what you're saying, thank you.
Okay.
Could you explain one more time how you got the minus DTOH over DT to just equal K as a concentration of chloroform and hydroxide? Is that just something that we can just take each of those expressions up there and set it equal to?
They both equal.
Okay.
So I think the one, because they say let K be the rate constant for the rate equation in terms of just hydroxide, the 1/7 or times 7 is built into that K, and then you're finding the relationship to the other ones.
Yeah.
Using, right? So like,
by factor.
Because rate is always constant times the concentration, so then this is just saying that
Right.
K is equal to the negative.
That's just because it's a reactant, if it's product.
so K would be different if they said let K be the rate constant for in terms of chloroform, right?
Yeah.
Right, it would be something different when you calculated it.
Yeah. Yeah. And then you'd be relating that. Then you'd be indexing off of it to figure out the hydroxide.
Okay.
So really here, Ryan, we're saying all we're saying right there is what is the rate of the change of the hydroxide ion concentration with respect to time. That's it. Okay, it's irrespective of the coefficients at that point. But then when you do relate that rate to any of the other ones, you have to keep the stoichiometry involved because they are linked. They're in a chain. They do react in a stoichiometric ratio to one another. Okay, let's go back. All right, so here's what we have here for, this is second order in a reactant, A. Here's my next slide. Okay, this is where I'm going to add one more simple little exercise for you to do with the homework. Here is summarizing zero order. The rate is equal to K. Here's the integrated zero order rate law and the half-life. First order with respect to one reactant, rate equals K times the concentration of that reactant. And you go through the derivation of it and integrate it, and you get, this would be more or less the log of A at some time t equals the ln of the initial concentration minus kT. Here's the second order reaction, K times the concentration of A squared. And you get, and this again would be the 1 over AT equals 1 over the initial concentration plus KT. And it shows you the equations for the half-lives. And what we pointed out on the first order, the half-life is independent of the concentration of the reactant. Doesn't depend on that. So this is really where you get this half-life concept in radioactive decay. The other thing to keep in mind is we're putting these three equations. This is what we want to kind of figure out. What is the concentration of A at any particular time? It's indexed off of what is the initial concentration. And if you just think of this, think of that arrangement for a second. Let's rearrange these. So this, let's look at it over here. And if we just rearrange that equation, we have AT equals negative KT plus the initial concentration okay, go away. This one would be the natural log of the final concentration is equal to negative KT plus the natural log of the original concentration. And this one is 1 over the concentration at any time t is equal to KT plus 1 over the initial concentration. All right? So here's your y equals mx plus b. Y equals, so your m here is negative k. It's going to have a negative slope. T plus ln of, and there's your b, that's your y-intercept. Y equals, so the slope here is negative k, t is x, and your y-intercept is your initial concentration. Okay, so I'm not going to belabor this one a lot. This is another, and see if you can do this in about 10 minutes, not right now. You can do it on your homework. Here's even a sheet of paper, a sheet of graph paper, and you can staple it to the back of your homework when you're done with it. And why I say see if you can do it for 10 minutes, because I intend to have something similar on the final, some similar data. Here's the deal. You look at this data, you take this data, you can see it's all in 5 minutes. It's giving you all the data in terms of the concentration of the, so the A naught, the ln of the A naught, or 1 over A naught. Okay, so it's giving you these numbers.
So you find which one's linear.
Yeah, you're basically going to find out which graphing all that data. So you're going to graph, this is y versus time. Y versus time, Y versus time. You're going to make those three plots. You can make them all, it'd be best to just make them all right on this sheet of paper. So try to scratch out enough that you can get your three plots right on there and plot all three of them and see which one's linear.
So on the exam, we could make plots, I guess, or can we just look at the, I mean, kind of look at the numbers and be like,
You can tell if they're linear or not.
tell which one's linear, right? And you know that's the
But this is
order.
a different type of graph. You should double look at the table. Because it's not just a regular concentration and rate.
No, yeah, it's ln, so it's like set up perfectly for you to look and make sure it's linear. So I mean, right, this is the y, ln of a, and these are your.
Which one do you think they were?
So I mean, you can tell that
Okay.
that one's linear.
0.2, 0.3.
And
Well-
so, like, I guess on the exam, are we gonna have to draw out a chart? Is that gonna be part of the question, or is the question have to be like?
Probably. Why don't you plot them, and, I mean, just scratch them out
Yeah.
quickly and see what it looks like. Mainly to demonstrate that sometimes you really don't know the order of the reaction right away, and there may be such a scatter in the data that you really do have to graph it to see
Yeah.
which one is more linear.
I think it's because we have 1, 2, 3, 4. Like,
So we're saying that depending on which one is linear, that depends on which equation we're going to use, so that tells us what's the overall order of our reaction?
Yeah, whichever one of these gives a linear plot would point to it being
Meaning
that order.
over second order, we can't do it.
Well, it's not going to get any more complicated than that.
All right.
0, 1, and 2. We're going to talk about other things, pseudo first order, and we're going to talk now about first order in 2 reactants. So here, even here, talking about a second order, it's second order in 1 reactant. Okay. So which... All right, that's basically what a few of these slides are talking about. Just how are you looking at it as a y equals mx plus b. There's your data right there. Is that right? Yeah, that's your data. And then determine the order of that reaction. Okay, this is first order in A, first order in B, second order overall. Okay, so here's where it does get a little more, starts getting a little bit more complicated. That general reaction, so the rate is -1 over A times the change in A with respect to time equals -1 over B times the change in B with respect to time. Here's your rate equation, K times A times B. A to the first power, B to the first power. And through some double integration of this with respect to A and B, you get down to this, this arrangement here. This equation. This is second order overall. Okay, so that's second order overall. I'm not sure if any of the homework assignments have that equation, but that would be a second order overall expression. Okay, and the author points in here, rate laws can get very complicated very quickly. You can have rates like this. The rate is K times A to the M, B to the N. And so this introduces a pseudo first order concept. What do we mean by pseudo first order? If you had something like this where both A and B are impacting the kinetics, let's say it's first order in A, and it may be first or second or whatever order in B. To get to a pseudo first order rate constant, you could run this reaction at a very high B concentration. So now you would run the reaction with a really high concentration of B, so that, let's see, I don't know, if you start out initially, you've got really, really high B and a reasonable concentration of A. As A diminishes, B, the decrease in B is almost imperceptible. A is going down, and A may be going down 10%, B is just going down a little bit, 1%, 1/10%. So it is pseudo first order. You could actually kind of look at how is this reaction going, and B is just going to trail off real slowly because it's such a high concentration. So that makes the B part of the rate equation essentially a constant, or close to a constant.
What are the M and N? Like, I guess.
That would be the order of M, A, and B.
Yeah. So like, why are they saying it's pseudo first order?
Well,
N could be anything, right?Uld N be 2 and be a pseudo second order, or is that not? Okay.
I think it gets too complicated. Really,
Okay.
it's the most common way of approaching this here is where it is first order in A.
We're saying M and N are both 1 in this case. Right?
Yeah, most likely. But I mean, in general, you could go at it this way, but it gets a little complicated. I guess I'm getting off of it right now. But so if you, for M equals 1, you can do this pseudo first order approach to it.
Wait, so are you saying as B gets really small or A gets really small?
As B is very large.
Oh, large.
Very large. You work with a very high concentration of one of the reactants, and you look at the kinetics of the other. And so you get a rate constant here that is not the first order rate constant. It is the pseudo first order. So K prime does not equal K. It is a pseudo first order rate constant. So it would only apply in a case where the B concentration was very high.
You should put a slash through the K prime. It's not.
Yeah, good. All right. All right, this is basically to make one point. We started out at the beginning of the chapter, and I said thermodynamics will tell you, the energy changes and things like that in a reaction, but not be able to predict the rate of a reaction. That the kinetics and the thermodynamics are somewhat separate. But if we take a look at equilibrium, see, we haven't been looking at equilibrium. We've been looking at the initial rate of a reaction. If we start out with, uranium, 50 grams of uranium, and it's decaying in a first order manner, it's just what's happening initially there, I need a chemical reaction. We're not talking about the equilibrium. We're just talking about the initial rate. But if we started looking at equilibrium, at the start of a reaction like this, A goes to B, there's no B. Initially, at T equals 0, B equals 0. There's no B. So there's really no reverse going on initially. You have A going to B. But if B can decompose or react back into A, as the reaction proceeds, you start getting a reverse rate. You have B converting into A at some rate. You have A reacting to form B at some rate. And so if you start working down through this, if we looked at, here's where we have this negative, we moved it over here, the rate of change of A with respect to time is the negative this rate plus the rate of that. Grant?
So those other problems we were doing, do those account for this reverse reaction already just within, like, say we were given data, so like you measured how much you had at a certain time, that kind of accounts for the reverse reaction already happening?
Well, I think most of the problems we've looked at up to this point have all been looking at the rate, well, you're saying these other equations, they're basically looking at the concentration. No, they haven't been taking this into consideration. It's been only looking at the forward reaction.
Okay.
We've been starting out with a certain amount of A and saying, starting there, what is the rate of change of the A concentration with time? There's no B and no reverse reaction going
So
on.
how are we going to know when we need to include the reverse and when not to? This would be talking about opposing, this is kind of an opposing first order. It's opposing first order reaction. In other words, you do have a forward and a reverse. Okay.
Some of the, like uranium decaying, there's no reverse to it.
Yeah.
And there's other chemical reactions too. Methane burning to form carbon dioxide and water, it's a forward reaction. We don't have it going back. So now we're starting to expand it now. What if we had opposing first order, actually had an equilibrium possibility, situation that could be.
This is only for first order.
First order in both A and B. Right now, yeah. So, and you can pick that up right here.
So let me specify it in like a problem if it wants to do reverse reaction. I mean, obviously, if it's like radioactive decay, it's not going to be reversed. But okay.
Yeah, this would be kind of talking about an opposing first order reaction. Okay, let's just, all right, so yeah, so A initially, the initial concentration of A is B plus B at some time, A at some time. All right, so B at some time is A naught minus whatever A is at that time. There is a relationship between these. Let's just go on to, this is all this situation here. And let's not belabor it, but you get to a point where you can define everything from that. Because of this, we can now plug this relationship in for BT in this and get BT out of there and be describing everything in terms of A initial and A at some time T. And you get these expressions for a competing or a opposing first order kinetics. Okay, we're continuing to go down through here. Oh, I'm sorry, went the wrong way. So now the B at equilibrium, the concentration of B at equilibrium divided by the concentration of A at equilibrium, so you let this reaction go a long time to where it actually gets to equilibrium, is now the equilibrium constant.
Too many K's now.
Well, there's too many K's, but the beauty of this here is that the kinetics and the thermodynamics are converging on one another. Kinetics and thermodynamics are converging when you get out to equilibrium, and you can get to an expression that actually relates the equilibrium constant to the forward rate constant divided by the reverse rate constant. Here's your kinetics, here's your thermodynamics. When the reaction actually finally reaches equilibrium. And let's see. Okay, so that's the main point there, and you can look at that. I forget what section that was. That's section 20.4. It's really worth tracking down through there and see that there is a place where thermodynamics and kinetics kind of come together. We started out saying these are kind of two separate fields. You can't predict the kinetics from the thermodynamics. But when you actually get out to equilibrium, there is a relationship between the equilibrium constant and the forward and reverse rate constants. All right, now dig in a little further into this. Here is we're going to look at parallel and consecutive. Let's look at parallel reactions first. A can react to form B, or it can react to form C. It can do either one. And it does each of those at different rates. There's your rate constant for the conversion of A to B, and there's your rate constant for your conversion of A to C. So the rate of the appearance of B with respect to time is K1 times your concentration of A. Change in C with respect to time is K2 times A. You can get to expressions, we're not going to dive into the derivation of all of those, but you can get to
this in the packet, like an additional packet for us, because I think
Oh.
material shops.
I'm sorry. Here it is.
I'm wondering, I'm a little bit lost.
Sorry. I had it up there and forgot to hand it out.
Can I get the homework after class as well?
Yeah. A lot of equations here. Sorry. Thank you, Liz. Liz has asked some strategic questions this semester. Strategic, helpful questions. Sorry, we already went through about 12 slides already. Okay, so here's your parallel reactions. And we're not going to do necessarily problems on this, but I want to just pull here's a couple of points out of it. So parallel reaction. We're starting out with A. We have no B or C. At time 0 right here, all we have is A, no B or C. So, and remember, I said that the B and C do not form, they have their own independent rate constants, their rate of formation. So they're not going to follow the same line. You can see in this particular case, C is reacting, A is reacting to form C faster than B. And you have that situation right there. You've got all of these, eventually you have all of these things going on. You have, can have A going to B and B reversing back into A going to C, C going back into A. So you'd have 4 different rate constants. Let's see. In this particular graph, the rate of formation of, well, let's just compare it to one other graph here. Here's one where, again, we start out with A, no B, and no C initially. But in this particular case, the K1, the formation of B from A is very fast, but the reverse reaction once you get a certain amount of B in there, the reversion of B back to A is faster than the reversion of C back to A. And you actually see that early on in the reaction, B is at a higher concentration than C, but as they get to equilibrium, it reverses itself. And so that is, these reverse, the KR for B going back to A, the KR for C going back to A, the KR for B going back to A is much higher than that one. And so you have this dropping back down and you get a different amount of concentration as those three later on in the reaction. And so they're saying it's thermodynamically controlled. C may in fact be a much more stable compound than B. C is a more stable compound than B, and it ends up at a higher concentration. All right, one last concept to touch on is the temperature dependence. Rates of chemical reactions are strongly affected by temperature. This is the Van Hoff equation. It's 20.48, so it's in chapter 20, but it is really, and they mention it, it just doesn't give you the reference. This is the same equation we saw in chapter 5 before we talked about kinetics at all. And this K is the equilibrium constant K. They bring it up here because Arrhenius looked at that equation and he started looking at kinetic data and saying that he made an analogy between the rate constant K, not the equilibrium constant K, and instead of the delta H of the reaction, the activation energy. This is where I'm not sure if Arrhenius is the first one to propose an activation energy, or if based on the discussions at that time, he developed it further to this point, saying that, well, that activation energy is a little bit like an energy change, an enthalpy change in the reaction. And he came up with this equation, the Arrhenius equation, to relate the rate constant to an activation energy. Don't go from here to here. Come down through here. It's probably the best way, the way the book, this is the way it's laid out in the book. Here, rearranging it to here, getting it to this equation. K equals A times, A is the integration constant. This is an integration constant. If you do the integration of this, you're going to have a term coming up, and that's this one, this A. And another way of looking at it would be to take the natural log of all of this. Natural log of K equals natural log of A plus EA over R times 1 over T. And they're setting it up in the Y equals MX plus B format there. For the effect of temperature on rate. Effect of temperature on rate. There's a lot of factors in here. Your homework doesn't have a problem like this, but you've heard, that temperature, and know that temperature affects rates of reactions, but there is a mathematical way to treat that and predict that. Is that my last slide? It's my last slide. Let's look at the homework again for a second.
We're looking at number 8.
Yeah,
We should also look at 4 or 5, because they're very similar.
And very different.
And very-
different from anything we've done.
Yeah.
I should go answer for 6.
There is.
okay, let's look at 4. 4 and 5 can be handled similarly. So let's see where I have 4. 4. Let's read it. At 500 degrees C, dimethyl ether, or designated now as DE, decomposes according to the equation. So here's your dimethyl ether to methane, hydrogen, and carbon monoxide. Following data were obtained. So not a lot of data there, a little bit of data. So let's look at, let's set up a little table here. Total pressure. We're going to have the pressure of the dimethyl ether, the methane, the hydrogen, and the carbon monoxide, time 0. The total pressure is 312 millimeters of mercury. So what's the pressure of the dimethyl ether?
312.
All right. And what's the pressure of the other 3?
0.
Oh,
So now at 777 seconds, the total pressure is 488. We know that. So let's just say that the methane is pressure X. So these are going to be X.
This is ideal, we're assuming.
Yeah, assume ideal behavior. So what is the pressure of the dimethyl ether at 777 seconds?
312 minus, or 488 minus that? No. No.
312 minus that.
Yeah, 312 minus X.
But the total pressure increased.
But that's,
So more moles around the right side.
Let's say for a second, let's say we started out with 1 mole of DE.
Yeah.
And
You get 3 moles.
you're going to have, at some time here, you're going to have 4 gases. You have 4 gases contributing to the total pressure. You started out with only 1 gas. So each one of the total pressure is going to be the partial pressure of the DE plus the partial pressure of the methane plus that, right? And for every one of these that decomposes, you get one of each of those, right?
Yeah.
So let's see. You would have,
Like it's gotta be just minus.
so as the pressure of these goes up, the pressure of this one goes down, right? So this one is going to be 312 minus, let's see, what is that going to be? That's going to be, yeah, this is going to be 312 minus X.
For every 1 X, you get 3 additional X's, but yeah, that's
So the total pressure is going to be 312 minus X plus 3X,
Alright.
right? Total pressure? So that's going to be 3 So 488 is going to be equal to 312 plus 2x.
Yeah.
24.
This is X 88, so.
Yeah, I got it 88, so D is 224. And the
Okay, there you go. Calculate the partial pressure of DE after, so that is going to be 224 millimeters of mercury.
As you approach getting K, can you get them all turned into moles? Or molarity or?
The reaction is first order with respect to dimethyl ether.
Well,
So are we allowed to put pressures in for concentration?
Yes.
because they're the same thing, the mole fraction, you interchange partial fractions and mole fractions. So,
You can actually put in any unit you want to as long as they're both
the same.
are the same. You can use percentages, molarities,
Oh,
grams.
Anyway. Right.
Yeah, K, no, K isn't uniless.
No, it's not. It's
It can be different things. So, and it's telling us it's first order, and first order reaction is, where'd my stuff go? Is, we've got
So we need to
the
calculate.
ln
Right.
of A naught over AT equals KT. And so the log of DE initially over DE at time t is equal to KT. And so we know everything, and we know everything but that. We now know that initial concentration, 312 millimeters, 224 milliliters, and 777 seconds. And you can calculate K. So that knocks off A, that knocks off B. And then hunt for the expression for the half-life for a first order reaction.
Did anyone calculate K?
RT is 777.
Okay.
Took me a second or two.
4.26 times 7 minus 4.
I got that.
Then I tried to do it a different way.
Yeah, just take the, so it's going to be,
So what half-life would just be taking 312. Half of it.
Like a 0.63 thing. It depends on the order of the react. It's first order. So, I think the equation for first order is like 0.63.
0.693 over K.
that .693 is the natural log of 2.
Yes.
Yeah.
Natural log of 2 over
So
K.
what's the equation for half-life?
Natural log of 2 over K.
Yeah, so can't you use the same equation, just say natural log of 2 equals the constant?
Yes.
Yeah, what did you want to cut out of question A?
Okay, well, let's see. And then calculate the time required for the total pressure to reach 700 millimeters mercury. Well, you can work through that. You work through 4. 5 is very similar.
Okay, calculate slightly.
5 is similar, except it's a different rate equation you're going to be using.
Is that seconds?
It's a second order. Number 7,
1630.
you can omit.
No, we're not doing 7.
Yeah, you can omit 7. And number 8, you can omit C, D, and E. But you should do, oh, and I'll give you a couple hints on number 8.
So skipping number 7 entirely.
Skipping C and D for 8.
Oh, a couple hints. Where are my hints?
Okay, it's just 7.
6 is easy.
Nice.
Oh, well.
5 would be the whole thing.
5 should
I got to give you this homework here, but,
More homework?
no, I got to give Grant. But what I was going to tell you on number 8,
And so calculate D.
okay, number 8, use equation 20.47 for A, and or look at those. That equation should help you. And look at equation 2017 for B. It's just a half-life. So those 2 equations would help you on number 8.
All right, thank you.
All right? And these are due Monday. All of it's due Monday. And we'll finish chapter 20 on Friday. Try to. Okay, we still got a couple concepts. Reaction
What are we
mechanisms.
doing after?
Review? We only have 2 classes after.